Okay, welcome back. Now I'm going to revisit the problem that we did previously with the styrofoam cup, and then I had one with the styrofoam cup was in the aluminum cup, and I said if the source of heat, the loss of heat is primarily due to conduction, how many minutes will it take to go from its original temperature? Its original temperature was 75.4 Celsius, and then I said how many minutes will it take it to cool down to 50 Celsius. And then when we ran the experiment, we noticed that the aluminum and the styrofoam together were a bit slower, and they took 19 minutes. So the aluminum and the styrofoam took 19 minutes to reach 50 Celsius. Okay. And the styrofoam alone, in that same time, 19 minutes, it had cooled down to 49.2 Celsius. So the styrofoam had cooled quicker. When we did the theoretical prediction of the conduction of heat, we got something like 27 minutes, T theoretical. 27 minutes. So that got me thinking, what were some of the primary sources of error? Well, one of them I had mentioned in the video, the thickness of the bottom portion of the cup was thinner than the sides, so we had assumed that the bottom is also the same thickness. So that's going to cause both of these to cool quicker than the theoretical result. But also primarily we had ignored the radiation of heat through the top. Radiation of heat through the top. So now my question is going to be, what if we count the radiation and the conduction, if we count both factors and calculate the theoretical time that it's going to take to cool down to 50 Celsius, are we going to get a number closer to the 19 minutes? So I went ahead and measured the diameter of the top. The diameter that we had was the diameter of the middle portion, and the diameter of the top was 6.4 centimeters. So that's going to make the radius 0.032 meters, right? So then the surface area of the top, and then that's the radiation is primarily going to happen through the top. The surface area is going to be pi times 0.032 squared, okay? So then my question is going to be, how long is it going to take the water to go from 75.4 to 50? Okay, and then the calculation that we're going to get is going to be applicable to both the aluminum and styrofoam and the styrofoam, since the two times are pretty similar to each other. Okay, so let's see what we have here. So in the previous calculation, after we put in the conductivity of aluminum and the conductivity of aluminum and the surface area of the water with the cup, we got something like this at the end. 0.19 T minus 26 is equal to, then we got here minus mass of the water, specific heat of the water, delta T over dt. Then we took this and then we integrated and we got an ln function, right? So what's going to end up happening? How is radiation going to affect this? This number on the left, I'm going to have to add to it the power loss due to radiation, right? So I'm going to add 0.19 T minus 26 plus the surface area of the top, the emissivity of water, the sigma, and T to the power 4. Then I'm going to have here minus MWCW dt over dt. So I'm going to erase this. So we know that we're hoping that when we do this calculation, that the answer we get will be closer to 19 minutes, right? So 19 minutes was the experimental time. Okay, so then what's going to happen? Well, we put in all these numbers, but because we have a T to the fourth now, we have to be in Kelvin. So therefore, this 26 Celsius, we have to also convert to Kelvin, and from now on, do all our calculations in Kelvin. When it was only conduction, we could have kept everything in Celsius because it only depended on delta T, the change in the difference in temperature between the inside and the outside. So now I'm going to have to convert that to Kelvin. 0.19 T minus, and then 26 Celsius will be what? 273 plus 26, that'll be 299.15 plus the surface area, which is going to be pi times 0.032 squared, right? Times the emissivity. When I looked up the emissivity of water, it gave me a result like around 0.98. So it's almost acts like a black body. So we put here 0.98, okay? Then we put the sigma value, 5.6696 times 10 to the minus 8, right? And then we put t to the power of 4. But on top of the fact that it's radiating based on its temperature, right? Because the surrounding, it's also absorbing heat from its surrounding, right? So you have to do here t to the 4th minus t of the surrounding temperature to the power of 4. Okay, then I'm going to set that equal to minus mass of water, specific heat of water, dt over dt, right? So then I'm going to have here 0.19, so then 26 is going to be 299.15, 299.15 to the power of 4. So it's radiating based on its temperature to the 4th, and it's also absorbing from its atmosphere based on the atmospheric temperature to the power of 4, right? So then that's the amount radiated and absorbed. This is the amount of heat that is conducted through the walls of the styrofoam, right? Then that's going to equal to minus the mass of the water. The minus the mass of the water is the same as before, 0.1015 times 4184 dt over dt, right? So when we multiply that out, we get integrate from the initial temperature. The initial temperature was 75.4 in Celsius. We're going to add here 273.15. In Celsius, this is going to be 348.55. So the initial temperature, 348.55, all the way to the final temperature, which we wanted to eventually reach 50 Celsius, right? So 50 Celsius is going to be 50 plus 273, 323.15. Okay, now if we want, we could just simplify this a tad bit. We could multiply 0.19 times t, distribute 0.19 with this, and also distribute this into this. We get here 0.19. Okay, so let's put all of this in. T is equal to negative 424.676. And then when you do the integral, it comes out to be negative also. So the two negatives cancel and give you positive. It comes out to be negative 3.3924. Okay? So of course the two negatives cancel. So we multiply this by 424.676. Okay? So that's going to give me 1,440.67 seconds. We divide that by 60 seconds. That gives me 24 minutes. Okay? So it does reduce the time quite a bit, right? So with just conduction alone, it predicted that it should reach 50 Celsius in 27 minutes, right? 27 minutes. Now, if I include the radiation through the top of the cup, it's predicting 3 minutes faster. So 24 minutes. Now, of course, when we ran the experiment, it took 19 minutes, okay? So the fact that it took 19 minutes, well, those are all other kinds of sources of error, right? Primarily due to the fact that the bottom of the cup is much thinner, right, than the thickness through the sides. And there are other sources of error like heat loss due to convection, right? There's also heat loss due to convection, and other sources of maybe experimental error, such as maybe I didn't measure the thicknesses right, I didn't measure the diameters and all the other sizes right. So that extra 3 minutes did help us, and it gave us a closer answer to our experimental, but there are also other sources of error. So you can see here how to bring radiation and conduction in at the same time, and how to do this complex calculation and put it in an integral and then calculate the total time. Okay? Thank you very much.